Okay, hi everyone. Today I'm going to be going over the 2018 AMC 8. Since there's only like 3 or 4 of you, I figure I'll go through the problems as normal, but like maybe I'll ask you right now um, which problems you wanted to go over in advance, or like if you have any problems that you want us to go over first. I figure we have time to get to every problem anyway. But if there's a problem you want to go over first, just let me know. Yeah, otherwise, we'll get started. Just pull up the annotation. All right, so we'll start with problem 1. We have an amusement park, does everyone have the problems? Actually, I should probably just make sure. I would send a file if I knew how to. Oh well. If anyone doesn't have the problems, just let me know. But you can also just follow along, obviously. Okay, problem 1. So we have the United States Capitol, which is 289 feet, and the amusement park has a ratio of 1 to 20. So we want to know what the height of the replica would be to the nearest whole number. So what we know is that the original is 289 feet, and we're multiplying by 1 replica foot for every 20 feet that it is in actual life, like in real life. Right, so we're multiplying by 1 over 20, and this is the same thing as just dividing 289 by 20. This is going to get us 14 14.45. So now we just have to see which of these whole numbers it's closest to. Since this is less than 14.5, it's going to round down to 14 instead of up to 15. Okay, problem 2. So we have this product, and we want to find its value. So I'm sure you've all learned about FOIL. So it's sort of this A plus B times C plus D. And basically you can make a box where one of the sides is A plus B, the other side is C plus D. And so if we found the area of this rectangle, it would be A plus B times C plus D, since the area of the rectangle is the length times the width. And then we could calculate each of these boxes individually and add them up. So like this would be A times C, and this would be B times C, B times D, and A times D. So we could use FOIL on like 6 times, but that would be extremely slow, right? So we want to look for a pattern. And right away we notice that we always have 1 at the beginning, and we have these fractions that are sort of increasing in denominator, right? So we'll just look at the first one. It's 2, right? Next one is 1.5. Next one is 1 1/3. So I'll write that as 1.33. This line just means that it repeats. So we could do this for every single number. Still doesn't seem to be that great, right? But if we convert everything to an improper fraction, we see something quite nice. So we have 2 over 1, and then we just change this to an improper fraction, and we'll do the same for everything else. And we can see that there's a 2 in the numerator and denominator, and because we're multiplying, we can just cancel this out. And we can do the same for everything else as well. That leaves us with a 7 on top and a 1 on the bottom. So the 1 doesn't matter because it's just 1. So we're left with our answer of 7. So you might have seen this method immediately, but I went over those other two methods so that you could kind of see like how you might arrive at this kind of solution. So any questions about that? Okay, cool. Let's move that. Okay. So we have 5 students, or 6 students, sorry. Aaron, Bob, Sid, Dan, Eve, and Fawn, and they start counting in a circle. And then every time there's a number containing 7 as a digit, or multiple 7, that person leaves the circle and the counting would continue. So there's not really any trick to this problem. We kind of just have to work it out. So we draw the diagram. This is a very bad circle. Okay. We just pretend they're in a circle. So we would have an Arn with 1, Bob would have 2, and we'll continue. So 1, 2, 3, 4, 5, 6. Arn has 7, so he'll be eliminated. And then we go 8, 9, 10, 11, 12, 13, 14. So because C has 14, they'd be eliminated. I'll just write down which number they get eliminated on. And then D has 15, E has 16, F gets 17, and they'd be eliminated because it has the digit 7. And then we continue 18, 19, 20, 21. So because 21 is a multiple of 7, we eliminate B. And then 22, 23, 24, 25, 26, and finally 27. As I said, there isn't really a trick to this problem. You kind of just have to figure it out, draw a diagram, and make sure you stay organized. Okay. Problem 4. We have a 12-sided figure that's drawn on centimeter graph paper, and we want to know what the area is. So we can see that there's sort of like a square that has a spike on each side, right? So the square in the middle is 3 by 3, so we know its area is 9. Now we just have to find the area of the spikes. So since each of the spikes is actually just a triangle, there's 2 triangles that are each half of one square, one small square. We can pretty much just put the 2 together. So like if we took this one, for example, and just put it right here, we would get a full square. So what that tells us is that each spike actually just has an area of 1. So we just add 1 4 times. So our answer is 9 plus 4, right? So 13. Okay. Any questions so far? Cool. Okay. So now we have a question that asks us for all the odd numbers added up to 2019, and then subtracting all the even numbers up to 2018. So obviously it would be a pretty bad idea to try to find this sum. Instead, we should try to find a pattern, right? So obviously odds and evens, that's a pretty clear pattern. So we can pair them up. So for example, taking 2019 and pairing that with 2018. So 2019 minus 2018, that would give us 1. And then if we did the same for 2017 and 2016, that would also give us 1. So we can continue this pattern, and all we have to do is find out how many pairs of numbers there are. And we can see that the pattern would end at 3 minus 2. So we have a bunch of 1s, and then 3 minus 2, and then just this extra 1 on the end. So since we have the largest number is 2019, and this 1 is sort of on its own, there are actually 2018 numbers that can be put in pairs. So we have 2018 pair numbers. So to find the number of pairs, we just divide by 2. It's 1009. So that means there are 1009 pairs of numbers. And since each pair evaluates to 1, we just multiply by 1. It's still 1009. And we just add the 1 at the beginning. We get 1010 for our final answer. Okay. 16. Okay. So we have who's on a trip to the beach, traveled 50 miles on the highway and 10 miles on a coastal access road. He drove 3 times faster on the highway, and we want to know if he spent 30 minutes on the coastal road, how many minutes his entire trip would take. So we can just sort of draw a table. It's probably best for this. So we can have 1 for speed, and we know that, let's call this column the highway, let's call him the coast. Right, so he's going 3 times faster on the highway, on the coast. On the coast, he's only going at 1 times his coastal speed. Highway is 3 times his coastal speed. And his time, spent 30 minutes on the coastal road. And then we have the distance finally. So I had 50 miles on the highway and 10 miles on the coast. And we need to know how much time he spent on the highway so we can find his total time, right? And so one thing we know is that distance is equal to the speed times the time. So if we look at the coast, he went 10 miles in 30 minutes, right? So what that means is that in an hour, he would have gone 20 miles. So that basically means that he was going at 20 miles per hour. And what that means is that on the highway, he must have been going at 60 miles an hour. So now we just use this formula again. The distance, 50 miles, is equal to his speed, which we know is 60 miles per hour, times the time. So 60 miles per hour, since there are 60 minutes in an hour, we can sort of think of this as 1 mile a minute. And that makes it a little bit easier to see that he spent 50 minutes on the highway, right? Because 1 mile a minute, if he goes 50 miles, that must have been 50 minutes. That's pretty easy to see once we simplify that. So that means that he spent 50 minutes on the highway. And if we add those two up, 50 and 30, we get our final answer of 80. Okay, this problem is a little trickier. Any questions? Just to recap, we sort of did like a U-turn here, right? So we went from the time on the coast to the speed, and then because we're given the ratio, we can find his speed on the highway, and finally find his time on the highway. Okay, cool. Problem 7, the 5-digit number 2018U is divisible by 9. We want to know the remainder when this number is divided by 8. So one trick that we know is that any number that's divisible by 9, if we add up all the digits, it must also be divisible by 9. So if we add up the digits that we already know, that's 11. And then if we add u, that must be divisible by 9. So u basically has to be 7. There's no other value that gets us to a principal of 9. Since we've already passed 9 and we can't get to 27 because u would have to be 16 and that's too big, right? It has to be one digit. Okay, so we know that the number is 20,187. And we just have to divide it by 8. So I'm not gonna care too much about the quotient because we're just looking for the remainder. So we would put a 2 up here. I'll put it out here anyway. The 2 times the 8 would be 16. So it's just using long division to figure out what our remainder would be. And then we multiply it by 5. And then another 2. And this would become 27. So then we would put a 3 down and we would subtract 24, which would leave us with a remainder of 3. Okay. Any questions about that problem? I can go over the long division again if you need. I can also draw it slightly less messy. Okay, cool. Let's keep going. Okay, Mr. Garcia is asking members of his health class how many days they exercised for at least 30 minutes. And we have a bar graph that summarizes everything. So we see that the y-axis is the number of students and the x-axis is the number of days of exercise. And we want to find the mean number of days of exercise last week. Always good to know what we're trying to calculate, right? And we're rounding this to the nearest hundred. Okay, so to find the mean number of days, we have to find out the total number of days and divide it by how many people there are. So we'll first find how many people are in the class. Let's do that. We have this 1, 3, 2. I'll label these 2, 6, 8, 3, and 2. So we'll add these up. 1 plus 3 is 4, plus 2 is 6, plus 6 is 12, plus 8 is 20. Add the 5 here, it's 25, right? So we have 25 people. Now we just have to find out how many days they exercised in total. So 1 day of exercise times 1 person is 1. 2 days of exercise times 3 people, that's 6 days of exercise. And we're going to continue the pattern here, multiplying the number of days of exercise by how many people. So 3 times 2 is 6 again. 4 times 6, 24. 5 times 8 is 40. 3 times 6 is 18. And then 2 times 7 is 14. So we add these all up. 1 plus 6 is 7, plus 6 is 13, plus 24 is 37, 77. And then we just add this 32 over here, right? That's 109. Okay. So now to find the average, we just do the total number of days divided by the total number of people. So 109 divided by 25. And that's 4.36. Because you can multiply it. It goes in 4 times, and then 9/25 can simplify to 36 hundredths. Okay, any questions about that problem? Okay, moving on. So we have Tyler, who is tiling the floor, I guess, and it's 12 by 16. He wants to place 1 by 1 tiles to form a border and fill in the rest with 2 by 2s. So we want to know how many tiles he's going to use. So if we just get a rectangle going and slightly smaller rectangle. Okay. So we want to know first how many tiles there are along the border. And when we're told that it's 12 by 16, so we can find that. Okay, so it's like 12, 16. So it can be tempting to just do 12 plus 16 plus 12 plus 16, and that would be 56. But one oversight here, right, would be that we're counting the corner tiles twice, since every corner gets counted both in a vertical side as well in a horizontal side. So since we only want to count the 4 corner tiles once, we'll just subtract 4. Basically, instead of counting each corner twice, we'll count it once. That's -1 for each corner, and there are 4 corners. So that's 52 tiles for this border. And now for the inside, right? Since we've tiled the border, each side now shrinks to 2 less than what it was before, since there's sort of a border that's cutting it off. That's not 16. Should be 14 now. So we want to calculate how many tiles are needed for this 10 by 14. Does anyone want to volunteer to say what the answer might be? Okay. In that case, I'll just go ahead and explain. It's sort of the same logic as the area, except we can just sort of divide each side by 2, because we can sort of treat the 2 by 2 tile as the new normal tile, and we'll only be able to fit half on each side. So like, instead of being able to fit 10 tiles along the side, we'll only be able to fit 5. Okay, well, I drew that terribly. 1, 2, 3, 4, 5. You can only fit 5 tiles along the side, and we'll only be able to fit 7 tiles along the width. So that would be another 35 tiles, 5 times 7. So we just add these up, and we have 87 tiles. There we go. Any questions? Okay. So problem 10, we're given that the harmonic mean of a set of non-zero numbers is the reciprocal of the average of the reciprocal of the numbers. That's a mouthful, right? And we want the harmonic mean of 1, 2, and 4. Okay. So it's the reciprocal of the average of the reciprocals. So the first thing we need to do is take the reciprocal of the numbers, right? We have 1 over 1, plus 1 over 2, plus 1 over 4. Kind of want to work backwards in this problem because the first thing we have to do is take the reciprocals of the numbers. And that's equal to 7/4. Right? 1 plus 2/4 plus 1/4. Okay, and now we need the average. Well, since there were 3 numbers, we just have to divide this by 3. And that would get us 7/12. Okay, and finally, we have to take the reciprocal again. That's 12 over 7. So C is our answer. Okay, any questions about that problem? Okay. Just one note, the harmonic mean is basically just one type of average. Usually when people say mean, they mean average, like arithmetic average sort of. like where you add all the numbers, right? But there's also different types, like geometric mean, where you would multiply all the numbers and then take it to some sort of root. So like with 2 numbers, you would take the square root of the product. With 3 numbers, you would take the cube root of the product. So there's different types of means. Okay. We have Abby, Bridget, and 4 classmates who are going to be seated in these X's. And we want the probability that Abby and Bridget are adjacent, either in the same row or the same column. Okay. So let's just imagine that, let's say this X is actually Abby. And we want the probability that Bridget would be in the same row or the same column. Well, there are 3 spots where Bridget could be, such that they were in the same row or column, as well as 2 spots that would not work. So that would be a probability of 3/5. Same row, same column. I missed something. Oh, my bad. That's my bad. Obviously, this doesn't count, right? Whoops. This doesn't count. Yeah. Adjacent has to be right next to each other, right? I just read it as same row or same column. So I gotta read the problem. Okay. So we've shown that in a corner spot, there would be a 2/5 chance, right? But there's also another case. The other case is where Abby is in one of the center seats. Let's say this one is Abby. Then there are actually 3 adjacent spots where Bridget could be, and those would all work. So we know that 3/5 is these sort of center spots. And we can't just take the average, because the chances that Abby is in a corner versus an edge is different. Right? There are 4 corner spots that would all be 2/5, but there are only 2 center spots that would be 3/5. So we have to take that into account. So what we do to do that is take 2/5 and multiply by 2/3. And we take 3/5 and multiply by 1/3. So this accounts for the probability that that specific arrangement happens. So this is basically saying there's 2/5 chance of being together, and that's only if they're on the 2/3 chance that they're in that Abby is in the corner. And the other would be 3/5 chance of being together, given that Abby is in the center. So we just have to add these up, and we can calculate that, right? 4/15 plus 3/15. Terrible 3, by the way. 7/15. Okay. There's our answer. Any questions? Hope I didn't confuse anyone. That was my bad. Okay. Let's keep going. Problem 12. We have the clock in Sri's car, which is not accurate and gains time at a constant rate. We're told that he begins shopping. One day, as he begins shopping, he notes that his car clock and watch, which is accurate, both say 12 noon. When he's done shopping, his watch says 12:30. His clock in the car says 12:35. And so later that day, when he loses his watch, the car says it's 7 o'clock, and we want the actual time. So the one key piece of information here is that clock gains time at a constant rate. So if we can figure out like that specific rate, then we'll be able to solve the problem. So we know that it took him 30 minutes to go shopping, but his car clock said it was 12:35. So his car clock thinks it took him 35 minutes, right? So because the car clock is gaining time at a constant rate, we can just do a ratio here. So the car clock to actual time is 7 to 6. So basically there's going to be 7 car minutes or seconds, however you want. So I'll use minutes. 7 car minutes for every 6 real minutes. Okay. And later that day, his clock says 7 o'clock. So what's the actual time? Well, we know that we can just swap these units for hours, basically. 7 car hours would basically just be 6 real hours. And 6 hours after 12 o'clock is 6 o'clock, obviously. And the reason I can change minutes to hours is it's the same thing as multiplying by 60, right? I can multiply by 60 minutes, or multiply by, it's just minutes over hours. And since I'm multiplying by the same thing on the top and bottom, this will work out. And I flipped the fraction, great. Well, you get the idea. You can just multiply by hours over minutes to swap the units. Okay, any questions there? Cool. Okay, Layla took 5 math tests, each were up to 100. We're told that each test score is between 0 and 100, and that she got the same score on the first 4, but received the higher score on the last test. You know, her average on 5 tests was 82, and we want to know how many possible values there are for Layla's last test. So if the average of 5 tests was 82, then we can find the total of all the tests just by multiplying by 5. And the reason for that is because to get the average, we would have had to take in the total and divided by the number of tests. So we're just doing the same thing in reverse. Okay, so we know the total is 410. And we want to know how many possible values there are for the last test. Let's just start from the beginning. Let's say she gets 4 zeros. And we can see that this doesn't work because she can't get 410 in the last test. Because that's over 100. So let's try something a little more reasonable, maybe 70. So 4 70s is 280. We're still a little off because that would leave the last test as 130. Okay, so we'll try 80. That's 320. And that seems to work because the last test would be 90. And this is also nearing the upper limit because we know that 5 82s in a row would not work because the last test has to have a higher score. So that basically means that the highest possible actually would just be 4 81s and 186 on the last test. Okay, so now we just have to find the lower bound for her tests. Her lower bound is going to be when she scores 100 in the last test, and that would mean the lowest score for all the other tests. So if we subtract 100, we'll get 310. And if we divide by 4 to get the score for each individual test, that would leave us with 77.5. That means that, obviously, since we have to have integers, we could do we would want to do 277s and 278s, but that wouldn't be allowed. So we're going to have to settle for having 478s and 98. We can't do all 77s because then that would leave us with 102 as the last score, and that's too high. So our possible scores for the last test range from, actually it's better to do the tests on the scores on the first 4 tests, because we can see that 78, 79, 80, and 81 all work. Each of these produces a different value for the last test, so the answer would be 4. And notice you could trip yourself up if you went by the last score. You see 98, and you would also see, what's the lowest one that we had? 82, right? Like, or 86 actually. So you might look at this difference and say that it's 12. So you might be tempted to pick something like 10 or 18 instead of the actual 4. Okay, any questions? Okay, cool. We have n, which is the greatest 5-digit number whose digits have a product of 120. And we want the sum of the digits of n. So we have 5 digits. Okay. Well, to make the biggest number, we obviously want the biggest first digit. So biggest digit is 9. But then we see that this isn't going to work because 9 is not a factor of 120. So there's no way we can get 120. So we'll just settle for the next best, which is 8. And 8 does go into 120, right? Because that's 8 times 15. So now we just need to find 4 numbers that multiply by 15. And we'll use the same logic that we did for the first digit. So we would check 9 first, but then obviously that doesn't work. And we can just see that for 15, it's going to have to be 5. That's the largest single digit factor. Okay, so now the other 3 digits have to multiply to 3. Using the same logic, we would want to make this one 3. And then the last 2 digits multiply to 1, so there's just 1s. So we find the sum of the digits 13, 16, 17, 18. Okay. So the most tricky part of this problem is just seeing that you want to, like realizing that you want to pick the biggest possible first digit, right? So because of how place value works, the first digit is going to be the most important for finding the greatest number. Okay, problem 15. We have 2 smaller circles, each of which has a diameter which is the radius of the larger circle. We're told that the 2 smaller circles have a combined area of 1 unit, so we want the area of the shaded region. Okay, so let's consider this radius. Right, we don't know what this is, so we'll just call it x. And now using the formula for the area of a circle, area is pi r squared. Each of these small circles would be pi times x squared. Okay, and we can double this because we have 2 of them. That's equal to 1. Now let's look at the large circle. Each of these is x, so it has a radius of 2x. Using the same formula again, we get pi times 2x squared, which is also equal to 4x squared pi. And we can see that the original way we had 2x squared pi. And because we're finding the area of the shaded region, we actually have to subtract this non-shaded region from the entire circle, from the big circle. So this 4x squared pi is going to be subtracting 2x squared pi for the shaded region. And that leaves us with 2x squared pi, which is exactly what we had for the non-shaded region. So that just tells us our answer is 1. So that's a cool fact. We now know that the area of these two circles will be equal to the area of this shaded region. And this will work no matter what the radius is, right? Because we used x. So we didn't actually have to find what the radius was for this specific circle. All right, any questions so far? Doing okay on time? Okay. So we have Professor Chang, who has 9 language books, 2 Arabic, 3 German, 4 Spanish. And we want to know how many ways there are to arrange the 9 books, keeping the Arabic books together and the Spanish books together. Okay. So we can treat this as basically a block of Spanish books, a block of Arabic books, and then 3 German books. That's a G. At least I wish it were. Okay. So we want to rearrange these books, right? Since we have 5 items, our leftmost item has 5 choices, and then 4, 3, 2, and 1. So we have 120 ways to arrange our sort of blocks and gerund books. Obviously, this is not our answer because we haven't considered how we rearrange our Spanish books. So for example, the Spanish books, there are 4 of them. We can arrange those 4 books in any order. That's the same thing as what we just did here, except without the 5. So 4, 3, 2, 1. That's 24 ways. And then with the Arabic books, because there are only 2, it's just one on the left, one on the right. You can think of it that way. That means that there's just 2 ways for that to happen. So to find our answer, we would just have to do 120 times 24 times 2. Right? And that would get us 5,760. Okay, any questions about this problem? So the key insight for this problem is noticing that you can group the books together, like the Spanish and the Arabic, and then just deal with those at the end. It'd be very hard to calculate that otherwise. Okay. If Bella begins to walk from her house to Ella's house, and Ella begins to ride a bicycle toward Bella's house. They each have a constant speed, and Bella rides 5 times as fast. The distance is 2 miles, and we're given that in feet. And we know Bella covers 2.5 feet with each step. So, how many steps will Bella take by the time she meets Ella? Okay. So we can just figure out how many steps she takes. We just have to take the total feet and divide by the number of feet that are covered with each step. So with each step, it's 2.5 feet. But we also have to consider that Ella is coming towards Bella 5 times as fast. And that's going to be counted because it's when they meet. So, right, because if you think about Ella biking 5 times faster, that reduces the amount of time Bella has to walk by a lot. So we have to add 5 times 2.5. So this overall is 6 times 2.5, which is 15. So now we just have to do some long division. So 15 doesn't go into 10, but it does go into 105, right? 7 times. We're just left with 60. Doesn't go in, or doesn't go into 6, so we put a 0. And then we would add the 0 with 4. Okay, there it is. Answer A. Any questions about that? Cool. Positive factors of 2, 3, 2, 3, 2. Okay. First thing we want to do is find the prime factorization, right? Start it up. Let's start it up here. And we'll start a factor tree. We have 2. You can see that 2 divides it immediately. And take out another 2. Let's get those. Cool. Just keep taking out 2's. I mean, I'll just make this faster for us. We'll just look it up. Or not. Okay. My computer's weird. All right. We'll follow through. Okay. So we have a bunch of 2's. 1, 2, 3, 4, 5, 6 of them. We have a 3. And we have 2 11's. So that's useful. But we need to find how many positive factors it has. So that's not immediately obvious. But if we think about what a factor of this number has to have, it's going to be 2 to the something times 3 to the something times 11 to the something. And we just have to figure out how many possibilities there are for those somethings. So for 2 to the something, it could be 0, 1, 2, 3, 4, 5, or 6. That's actually 7 possibilities. And 2 to the 0 is just 1, basically. So, and technically every other prime could be counted, but it would just have to be that number, that prime to the 0th power, should be 1. And that would always be 1 possibility. So it's not going to affect our final answer. So back to the factors we care about, 3 to the 1st power could either be 3 to the 0 or 3 to the 1st in our factor. That gives us 2 choices. For 11 squared, we have 3 choices. So just multiplying these together, we get 42. No, not 42. Is it 42? Yeah, that's right. Unless I messed up somewhere. No, I didn't. Okay, we're good. Any questions? Okay. We have a sine pyramid. Interesting. Okay. Each cell gets a plus if the 2 cells below it have the same sign, and a minus if the 2 cells below it have different signs. We have a picture, a diagram for a 4-level pyramid. We want to know how many ways there are to fill the cells in the bottom row to produce a plus at the top. Okay. So for this one to be a plus, well, that would basically mean that these two have to be the same, right? So let's stick with our example for now. There's obviously the other case where it's 2 minuses, and we'll deal with that later. Okay, so these two are both pluses. So these 3 have to, let's look at these 2. These 2 would have to be the same, and these 2 would have to be the same. So whatever this one is, all 3 of them are going to be that. So basically, we've just got two choices again. We could either do all minuses or all pluses. So once again, we'll stick with their example. They have three minuses, and they just go, and because all these have to be different, they do plus minus plus minus. And the other option, if we start with a minus, because of this minus, this must be a plus. And because of all the minuses above, we have to alternate at each step. So sticking with this minus, these minuses, we have two possibilities. Now let's see what would have happened if these were instead pluses. If these are pluses, all of the symbols at the bottom have to be the same, for the same reason that these ones are all the same when these are pluses. Because we can sort of draw the arrows. So that's another two possibilities. Either all twos or all pluses or all minuses. Okay, so that's all the possibilities when we have the plus case. The other case is when we have minuses. Okay, so when these are minuses, it's either, and this is a minus, this would have to be a plus. This would have to be a minus. So let's see how many ways there are to fill in the bottom now. This minus means that these two have to be different, but these two have to be the same, and these two have to be different. So we could either have plus minus, minus plus, or we could have minus plus plus minus. So that's another two possibilities. Now we'll go back up to the other case here. And these two are pluses instead. And these are pluses. These two have to be the same. These two have to be the same. But these two have to be different. So we could either do plus plus minus minus or minus minus plus plus. So we have 8, that's our final answer. It's not really a good way to do it that I see. Just have to stay organized. So keeping your cases organized and going layer by layer is definitely a good idea here. Okay, and keep moving. Okay, we have a triangle ABC, a point E that's on AB with AE equals 1, EB equals 2, with point D on AC such that DE is parallel to BC, and point F is on BC such that EF is parallel to AC. We want the ratio of CDEF to the area of ABC. All right. So the good thing about parallel sides is that it gives us similar triangles. So for example, because DE is parallel to CB, triangle ADE is similar to the triangle ACB. Similar, if you imagine this as like sort of an anchor point, then DE is sort of, it's like, you can take triangle ADE and scale it up, except everything is scaled with A as the anchor point. So when you scale it 3 times, this side AE goes from 1 to being AB, which has side length 3. So we've basically just scaled it 3 times up, right? And when we scale the sides by 3 times, the area is going to scale by 9 times. That's not immediately obvious, but if I give you a square with side length 1, actually don't have to do 1, let's say 3. If we double the side lengths, so that's 6, then looking at the areas, this is going to scale by 4 times when the side length only scales by 2 times. And so what you can kind of see is that because each side is scaling by the scale factor, the area is going to multiply with the scale factor twice. Once for the 6, once for the other 6. So that kind of tells you why if this is 1, then the area of the entire triangle is 9. So we'll call the rest of it 8 for now. And then looking at this triangle here, BFE is similar to BCA. And it's similar because, once again, using B as the anchor point, we can scale it up. Not as much this time, but by 50%. So because we multiply by 1.5, the area of this one is, we'll just call it 4. And we'll use this one, this side length 3, which means the entire triangle is 9. So excluding this 4 means that the rest of it is 5. This triangle is 1, so this is 4. Okay. The ratio of CDEF to ABC, therefore, would be 4 to 9. Okay, any questions? And my explanation of similar triangles is a bit wonky. I like using this anchor point to explain it, but everyone's confused. Let me know. Cool. Let's keep going. Okay. We want to know how many 3-digit integers have a remainder of 2 when divided by 6, remainder of 5 when divided by 9, and a remainder of 7 when divided by 11. Okay. So, great, okay. So one strategy that I like to use is just start listing them out. Most obvious strategy, but we'll do that. So this is 2 remainder 6, or remainder 2 when divided by 6. So this would be 8, 14, 20, and so on. Remainder of 5 when divided by 9, 14, and then 23, 22, so on. Okay, now we have remainder 7 when divided by 11. So we 18, 29, 40. And the best place to keep listing is in this row because it has the biggest number that we're dividing by. So it's gonna find the common number faster. So we keep listing. And 62 actually looks pretty good. Maybe it works because it has a remainder of 2 when divided by 6, right? And if we divide by 9, 54, okay, it doesn't work, right? So we have to keep going. But now we've found a number that has a remainder of 2 when divided by 6. So if we add 6 times 11, the number is still going to have a remainder of 7 when divided by 11. And it's still going to have a remainder of 2 when divided by 6. So it's actually going to be faster to just add 66 each time until we get the remainder of 5 that we want. So if we add 66, we get 128. Let's check divisibility, or let's check what happens when we divide by 9. So if we divide by 9, this is going to be 38. Oh yeah, that's not going to work. Okay, scratch that. You have to keep going, right? Because 128 divided by 9 is 12. Nope, not 12 remainder 2. Let's just do long division. There we go, 14 remainder 2. Okay, so we got to keep going. If we add, we can see that 66 has a remainder of 3 when you divide it by 5, or not, when you divide by 9. So that means that adding 66 one more time should get us what we want. Because right now we're at remainder 2 divided by 9. And if we add a remainder of 3, that should get us the 5 we need. So let's just confirm that. 128 plus 66, get 294. Let's divide it by 9 just to confirm. And we're off. Did I add this wrong? Dang, what am I doing wrong? Anyone see what I'm doing wrong? Oh, duh, I'm dumb. That should be a 1. My bad. Scratch all this. Okay, back on track. There's our 5. Everything works out, right? So 194 is our first 3-digit number. That works. We've already tried the other 3-digit numbers before, and we've seen that none of them are going to work. So to find the next one, we basically can do the same thing that we used to find this first one. Instead of adding 11 times 6, we'll add 11 times 6 times 9. Except we don't actually want to multiply all of those numbers. We want to find the least common multiple. So the smallest number that divides all of them. Because 6 and 9 share a common factor of 3, it's not just going to be multiplying them. So you kind of just see that it's 18. Another way you can do it is multiply them and divide by the common factor, which is 3. So we have 18, and we also have this 11, multiply 198. So we just have to figure out how many 198s we can add, right? So we can add it one time. We could add it twice. We could add it 3 times. Oh, that's not right. And we actually can't add it a 5th time because that would put us over 1,000 and into the 4-digit numbers. So our choices are add it 0 times, 1 time, 2 times, 3 times, or 4 times. That's 5 choices. Okay. Any questions? Sorry, I made that addition error. That was pretty bad. Right? Okay. Seems like there's no questions. Okay, we have point E, which is the midpoint of side CD, and we have BE, which meets the diagonal at F. We're told that the area of the quadrilateral AFED is 45. We want the area of ABCD. Okay. This is a midpoint. And cool. See what we can do. Oh. I think it's probably best to oh yeah. Can we do that? Let's try this. So I'll just ask everyone first. Does anyone have any ideas for what we could do? Like maybe what lines we could draw, what heights we could do. like altitudes that we could draw? If not, I'll continue. Okay. So in that case, let's start with this small triangle. Good places I need to start, right? So we have 45 and x. So that means that because this is a diagonal, 45 plus x is going to be half the area of the entire square. So we know the area we're looking for is just 90 plus 2x. And now if we look at these triangles FEC and FAB, we know that AB is twice of EC. So that means that they're similar triangles. Again, we have FAB and FCE. These are similar triangles again. Their anchor point is F, but they're not in the same direction this time. One of them is going in the opposite direction. That's still okay. We still have all the properties that we had before. So because AB is twice the side length of EC, its area is 4 times the area of FEC. Okay. So actually what we could do now is notice that the area of BEC is 1/4 the area of the entire square. And I'll just draw a couple lines to make that clear. So we draw this line. Because E is the midpoint, this rectangle has to be half the area of the square. And because BE is a diagonal of the rectangle, BEC must be half of the rectangle. So that makes it 1/4 of the entire square. So we have 45 plus 4x, and that's this trapezoid. And that's going to be 3/4 of the entire square. So to find the area of the square, we'll multiply by 4/3. Right? So if we divide it by 3 first, that gets us one triangle, and multiplying by 4 gives us the full square. So that's going to be 60 plus 16 thirds x. And now we just need to find the area, which would need to find x, right? At the start, we said that the area was also 90 plus 2x. So we can set these two equations equal to each other. Okay, we subtract 60 from both sides and subtract 2x from both sides. So we have 10/3 x equals 30. That means x is equal to 9. And we can plug 9 back into either equation, but either way, you'll get 108. Okay, any questions? I can go over any part of it in particular as well. Okay, let's continue. 3 more problems, I think. Yeah. Okay. So we have a regular octagon and a triangle formed by connecting 3 random vertices. Want the probability that at least one of the sides of the triangle is also a side of the octagon. Okay. Well, the first vertice that we choose can be any vertice, right? Let's just say it's this one. To make this a bit easier, let's calculate the probability that the triangle does not have any of the sides on the octagon, and then we'll subtract that from 1. So here's what I'm saying. 1 minus the probability of no side on the octagon is equal to the probability of a side on the octagon. And the reason for that is because the probability of no side plus the probability of a side has to be 100%. It's either one or the other. So let's find the probability of no side. With this first choice, we can't pick the vertices that are next to it. And there's, so now there's 7 remaining, right? 2 of these vertices right here, so I'll give that 2/7, and 3 vertices over here, I'll give it 3/7. And you'll see why I'm splitting it up later. If we pick one of these 2 vertices, then this vertex we can't pick, and the last vertex can be any of these 2. That's a 2 out of 6 chance because there are 6 vertices left. Now, I will fix this. Let's say we picked a vertex in the other 3. That actually crosses off 2 vertices instead. But it doesn't matter. It's still 2 out of 6. I don't think so. Might have had more choices before. Hold on. If we had chosen this one, we would not be able to pick this one. So yeah, we would have had 3 choices, right? Because we cannot pick any of the x'd-out vertices. Okay. So we have a 2/7 chance to get a 3/6 chance, and a 3/7 chance to get a 2/6 chance. So both of these actually multiply to 6/42. This is also 6/42. So we have 2/7. So we might be tempted to say, 2/7, there it is, right? Remember that we've actually found the probability of having no side on the octagon. And so what we actually need to do is take 1 minus that, get 5/7. Don't be fooled by 2/7. And the reason they put that there is because they know that people are going to use this method. I'll ask if there are any questions first. Okay, I'll talk a little bit about why this method is a bit better than like going through all the cases. So if we didn't use this method, we would have to find the probability of 2 sides on the edge, or 2 edges. We'd have to find the probability of 1 edge, and we'd have to add those up. And that's just a pain because we're basically doing twice as much work as we actually need to if we had used the other method. So using the other method, which we call complementary accounting, it's going to save you a lot of time. And a good indicator that you want to use complementary accounting is whenever you see the words at least. And it's not actually stated here, but it's sort of implied. Oh, never mind, it's right here, right? Okay, so the reason for that is because if we calculate it this way, we have to calculate 1 side and 2 sides. When we do complementary, we're just calculating 0 sides, so we're going to save time. Okay. Well, we have a cube with opposite vertices C and E, and then J and I are the midpoints of the edges. R is the ratio of the cross section to the area of one of the faces, and we want to find R squared. So to do this, we're going to have to find the ratio of their side lengths. Let's call the ratio, or let's call EH 1. So to the area of one of the faces of the cube, the area of a face is just going to be 1. So basically what we've done is we've just now made it so we have to find the area of this square instead of, and we don't have to worry about the division at the end. So let's see what this is. EF, well, that has a side length 1, and FJ has a side length 1/2. So we can use the Pythagorean theorem now to find this side length. Cool. Okay. Let's use the Pythagorean theorem. X squared, the side that we don't know, is equal to 1 squared plus 1/2 squared, which is also equal to 5/4. Okay. So that means that x is the square root of 5/4. And if we find the area of the square now, that's going to be square root of 5/4 squared. Okay. And now we just want to find oh, that's my bad. I've done this wrong. Okay. What we actually need to do, right, is to find, okay, so this is my bad. This actually isn't a square. Let's go back. Use EH is 1. Okay. So what we actually realize is that even though all the sides are the same, this actually isn't a square, it's a rhombus. So to find the area of the rhombus, we need to do one diagonal times the other diagonal divided by 2. Okay, let's do that. We could still, I don't know how useful this is. We'll keep this over here. Let's find the area, or the side length EC. That's going to be this triangle here. We're going to use this right triangle EAC. Okay, we know EA is equal to 1, and AC, find AC, we can use the Pythagorean theorem on this triangle, ADC. So AC squared equals 1 squared plus 1 squared, which is 2. So AC must be the square root of 2. Now back to EC. EC squared is 1 squared plus the square root of 2 squared. That's 3. So EC must be the square root of 3. Okay, now for JI. So JI is actually, because J and I are at the same height, it's the same thing as AC. It's just a diagonal of a square. Okay, so now to find the area of the rhombus, we just do √3 times √2 divided by 2. And the reason we do that, if I just take any rhombus here, okay. So let's see why it's a half. Okay. Basically, if I draw these diagonals, these are actually these diagonals are the same as the dimensions of the rectangle. So multiplying the diagonals, I get the area of the rectangle. So, and because each of these triangles is the same as the one flipped from it, so this one is the same as this one. This is this is this, and this is this. So basically, the rhombus is therefore half of the rectangle, right? So we have to divide by 2. Okay. So the area of the rhombus is √6/2. So now we just have to square and we'll get our answer. √6/2. Square, we get 6/4, which is 3/2. All right. What's your answer? Really sorry if I confused anyone with what I was doing at the beginning. I realized that this actually isn't a square. Any questions now? Or if you're still confused why it's not a square? Okay, on the last problem. How many perfect cubes lie between 2 to the 8th plus 1 and 2 to the 18th plus 1? Okay, so 2 to the 8th plus 1. Let's just calculate that since it's not too big. It's 256 plus 1. Right, this is probably a natural way you might approach it, just trying to calculate the smallest cube, the biggest cube, and see how many are in between. So the smallest cube larger than this would be 343. There's 7 cubed. But it's probably not that good of an idea to try to calculate 2 to the 18 and find a cube smaller than it. So we'll use the fact that 18 is a multiple of 3. So we can actually change this into 2 to the 6th cubed plus 1. And inside the parentheses is 64. And the reason this works is because 6 times 3 is 18. So this is actually just 64 cubed plus 1. So obviously the biggest cube less than this is just 64 cubed, which I'm not going to calculate. Okay, so we just have to find out how many cubes there are from 7 cubed to 64 cubed. That's pretty easy. That's just the number of numbers from 7 to 64. And that can be calculated with 64 minus 7 plus 1. So that would be 57, 58. And you just have to add 1 because we're including the numbers on both sides. And you can see they put 57 to trick you in case you forget the plus 1. Okay, I think that's everything. Any questions about specific problems? Or anything in general? Anything that I confused you with, maybe?